Hello, everyone. Thank you so much for coming. I know it's a beautiful Montreal day outside. The snow is melted, but thank you for coming into this room. It's my pleasure to introduce Jesse Davis and his talk on what is async, how does it work, and when should I use it. A round of applause, please.
Hi, everybody. Thanks. So this talk is going to be something more like what is async, when should I use it, and how does it work? Or perhaps a different ordering of that. The talk itself will be sort of asynchronous. So, oh, you guys liked that. So my name's Jesse Davis. I work for MongoDB in New York City. And as you probably know, in New York, we eat 3 kinds of food. We eat submarine sandwiches, pizza by the slice, and omakase, which is a Japanese word for something like, you go ahead and choose. It's when you go to a sushi restaurant and they just give you whatever is good that day. So New York is a crowded place, and each of these kinds of food has a different bottleneck as it tries to scale out to a very large number of clients. For example, with submarine sandwiches, it starts off, you go to the counter, and a sandwich maker comes out of the sandwich maker pool. And you tell the sandwich maker what kind of sandwich you want, what kind of bread, what kind of ingredients, and you have this one-on-one synchronous interaction that lasts for the duration of your request. So until the sandwich is complete, the sandwich maker doesn't take a break, doesn't talk to different clients. That sandwich maker is devoted to you until the sandwich is complete and you walk away with it. At that point, the sandwich maker returns to the sandwich maker pool until another client pops off of the eater queue. So the analogy that I'm making here is for a CPU-bound web service, something that might cryptographically sign your request or something like that. In that case, you can scale out by either making the sandwich maker faster by, say, arranging the ingredients more efficiently, or you might add more sandwich makers until the space behind the counter is full. So this is like you can add faster CPUs, or you can add more processes until you have as many processes as you have cores, but that's it. You don't want concurrency here. It wouldn't make sense for the sandwich maker to be switching between different clients and trying to make multiple sandwiches at once. So this is like a CPU-bound web service that doesn't request any external assets in order to satisfy a client request. There's no need for async here. Each process should just handle a single client request at a time from start to finish without doing any context switches. So this is when not to use async. Don't use async for subs. But different kinds of food have different scaling properties. So what about pizza? It starts the same as subs. You go in and the pizza cook appears, and you ask the cook for a particular slice of pizza. The slices are already made, but they're sort of lukewarm. So the cook takes your slice and puts it in the oven. And for the 2 minutes it takes for the slice to heat up, you're both standing around idly until the slice is hot, the cook gives you your slice, and you walk away with it. So in this case, how do you scale out the pizza cook? How do you deal with multiple clients showing up at once? Here, you wouldn't want the pizza cook to act like a sandwich maker. You don't want the cook to address a single client and then stand around idly for 2 minutes until the slice is hot, then give it to that client and then ask the next client, hey, what kind of slice do you want? If you had to devote a single pizza cook to each client, you would run out of space behind the counter before you run out of space behind the oven. So the analogy that I'm trying to make here is I'm trying to say that the cook ought to be async. The cook should respond to events as they occur. So as clients arrive, the cook asks each one what kind of slice do they want, and as slices become hot in the oven, the cook responds to that event and gives the hot slice to the client. And in that way, one or a couple cooks should be able to serve a very large number of concurrent clients. Now, the one problem that the cook is going to experience is that with lots of concurrent clients all asking for slices and lots of slices in the oven, the cook is going to need some kind of mnemonic for remembering how long each slice has been in and what client it belongs to. So this is sort of like a regular old web service that has a big, slow backend, like a database or an OAuth provider. Here, async is a great idea for scaling because a couple of processes can handle a large number of clients with many concurrent I/O operations. But you're going to need some way to store state while each operation is in flight, the same as the cook needs to remember which slice goes to which client and how long it's been in the oven. Now, this is even more true of omakase. Or actually, I just learned that it's probably pronounced omakase, but anyway. The way it works is you and your friends, you all go up to the counter, and the waiter tells the kitchen a bunch of people arrived. And that's it. The kitchen starts making sushi, whatever is good that day, and as the sushi becomes complete, the waiter ferries each dish to the clients at the counter. Once again, you don't want a waiter devoted to each client because you'll run out of space behind the counter. Instead, you should have one waiter or a small number of waiters who are event-driven, who notice clients arriving and notice sushi becoming ready and are able to multitask and scale out that way, up to the limits of the kitchen's ability to produce sushi. And this is like a WebSocket newfangled application where clients connect over WebSockets and await server-side events. So if you log into Gmail, for example, your browser opens a WebSocket connection to one of Google's servers, and then nothing happens. The connection remains idle until a new email arrives for you on the server. And then the server notifies you over the WebSocket connection and your browser updates itself. If Google's servers were to devote a thread for every client connection, they would quickly be overwhelmed by the number of threads that they had to support because WebSocket connections are very long-lived, so there's a very large number of them concurrently. For WebSocket applications in particular, it's critical to minimize the resources devoted to idle connections. So this is what async is for. It minimizes resources per idle connection while you're waiting for some event to occur. And the main resource that you need to conserve is memory. So we typically say that asynchronous applications are not CPU limited, but memory bound, and that the challenge is to store per connection state as efficiently as possible. The influential paper on this topic is called C10K. It's by a guy named Dan Kegel, and the paper's about 8 or 10 years old, but it's still a really good read. It starts off, so C10K is the term that he coined for 10,000 concurrent connections. And the paper starts off, it's time for web servers to handle 10,000 clients simultaneously, don't you think? After all, the web is a big place now. And he goes on to say that perhaps in the not too distant future, those who prefer using one thread per client will be able to use that paradigm even for 10,000 clients. Nevertheless, at the current time, if you actually want to support that many clients, you're probably better off using some other paradigm. So the orders of magnitude might have changed. It might be that 100,000, that maybe 10,000 threads is supportable now, but 100,000 is not. But the principle remains that if you devote a thread per socket, you'll run out of resources for representing those threads first and artificially limit your ability to hold sockets open. So if async is so great, and if the kind of web applications that demand async are increasingly common, then why is multi-threading still the conventional approach? Why isn't everything already async? And I think that the answer is that it's hard. It's hard to code. And the reason why it's hard is because when you're waiting for some event to occur on a connection, you need to remember what you were going to do when that event happens. You need to store state. So when a client request comes in and the server makes a related request to the backend, it needs to store state so that it remembers what it was going to do when the backend responds. And this is even more true of newfangled WebSocket applications, because in those applications, the wait is indefinitely long. When you visit Gmail, you don't know how long it's going to be before a new email arrives. So it's even more critical to efficiently represent that state while waiting for something to happen. And the conventional way to store state is with a thread. And with threads, you don't really have to think about how do I store state with a thread, because it's done for you. Threads store their state with the program counter, with the stack and the local variables in the current stack frame. The operating system and the programming language handle it for you, and you're used to that kind of programming model. Async applications usually use callbacks or some other representation besides threads for storing state while they're waiting for an event. And callbacks, while they're more efficient than threads, we're not used to using them, and they're not designed to be easy for this kind of use case. So it's much harder to keep track of what you're doing. Because threads and callbacks represent these two extrema of efficiency versus ease of use, there are a bunch of middle grounds that have been staked out in between the two. So there are coroutines, which are incredibly important and elegant and beautiful and awesome, and we don't have time to talk about them today, so that will be the exercise for the reader. There are also greenlets, which is what G-Event is based on, which are a little bit more like threads than coroutines are, and on and on and on. And the fact that we keep innovating in this area and making up new terms for slight variations on this theme of representing state in asynchronous applications, it suggests to me that no one of these techniques satisfies everybody yet. And so this is still kind of a live and developing area of research. So expect new awesome things in this area. But okay, right. So we've covered to some extent when should I use it, and we'll come back to that at the end again. But we can start to define what it is now. And what async is single-threaded, so it can't do concurrent computation, but it can do I/O concurrency. So a single-threaded async framework can have many I/O operations in flight simultaneously. It can be waiting for many things at once. It uses non-blocking sockets, and we'll see what that means in a few minutes. And it uses some platform-specific facility to register for event notifications on those non-blocking sockets. On Linux, it's epoll. On Mac and BSD, it's called KQ. And the final thing about async is that it uses an event loop to continuously process new event notifications and dispatch those events to event handlers, which are usually callbacks, but which might also be coroutines and so on. So when a random person says async to you, this may or may not be what that person means, but this is my definition of async. And when somebody says that Node or Tornado or Twisted or Tulip is async, they mean that those frameworks conform to this definition of async. So that's async in general. That's the general programming methodology that we call async. And now I'm going to switch to a specific library called Async IO, which is one implementation of this general idea. So Node is another implementation, so are Tornado and Twisted. About a year and a half ago, Guido started working on a new async framework called Tulip at the time, and that was the subject of his keynote at last year's PyCon. Since that time, it's been renamed Async IO. It's been merged into the standard library. Guido wrote it with help from like a dozen people, including me. I'm super excited and proud of that. The justification and specification for the Async IO standard library module is in PEP 3156, which is a surprisingly good read. And it defines both the standard event loop interface, and it also talks about coroutines, but again, we don't have time to talk about coroutines, so deal with that yourself. All right, so we're going to build an example application on top of Async IO. And the first thing we need to do is just kind of like look at a little screencast that I recorded of this thing in action so we know what it is we're building. And you can see that it's very standard. There's nothing special about this. It's just the stereotypical chat application. These are two browser windows that connect to the same server over a WebSocket. And when one of the clients sends a message over the WebSocket, the server rebroadcasts it to all of the other connected clients. Really straightforward, nothing special. So all Async IO applications are kind of built using the same set of layers. There's the application itself at the top, and the application uses a pair of abstractions to actually do the work. And the pair is a protocol and a transport. This is an abstraction that was defined by Async IO. It was heavily inspired by Twisted's design. And the distinction is that a protocol is something like HTTP or WebSockets. A protocol knows what bytes to send, and it understands the meaning of the bytes that it receives. And beneath the protocol is a transport. So TCP is a transport. And the transport knows how to send and receive bytes, but it doesn't know what bytes to send, and it doesn't understand the meaning of the bytes that it receives. Async IO is relatively low level, so it gives you transports like TCP, but it doesn't give you any protocol implementations like HTTP. So if you want a protocol, you need to get it from somewhere. I'm getting an implementation of the WebSocket protocol from a library called Autobahn. Now, beneath the transport is the event loop, and that's where we're going to be spending most of our time. The event loop finds out about events and dispatches the events to event handlers, which are callbacks. And the bottommost layer beneath the event loop is the selectors module. So just like Async IO, the selectors module is a new module in the Python 3.4 standard library. And it abstracts away all of the platform-specific differences between epoll and KQ and whatever the heck people use on Windows. And it lets you just kind of generally ask for event notifications without worrying about what kind of operating system you're running on. And for this talk, we'll consider selectors to be magic. We'll see what it does, but not how it does it. It's a layer beneath which we don't go. So now we can finally start to look at some code. This is in example.py. This is the chat application that we're building. And the first thing it does is it imports its protocol implementation from Autobahn. And in Async IO, you need both the protocol and a factory. And the factory knows how to instantiate the protocol one instance per connected client. So these two will hook up in a way that we'll see in a second. The next part of the example application is the chat protocol logic itself. So we have this global set of clients that represent all the currently connected browsers. And then we subclass Autobahn's chat protocol. And we override three methods. OnConnect runs when a client connects to us and we add ourselves to the global list. And then onMessage handles incoming messages from clients and rebroadcasts them to all of the other clients. And then the final thing, onClose, just removes us from the global list whenever a client disconnects from us. So really simple and stereotypical. What we're interested in is how does onConnect actually get executed in response to a client trying to connect to us? And my assertion is that if we've understood how the low-level event of a client trying to connect to our listening socket results in this callback actually being executed, then we've understood how async works. So keep that in mind. This is the goal. We want to see how onConnect gets executed. And we're going to get there in kind of two phases. So the first phase is we need to create a server and start listening on a socket. So that happens down here at the bottom of the example code. So we create the protocol factory. We tell it what kind of protocol to instantiate. It'll be the chat protocol that we defined. And we tell it to bind to an interface and listen on a port. And then the next thing we do is we get the event loop from Async IO, and we tell it to create a server. And we pass in the factory. And beneath that, we're going to tell the loop to start running. But we're not quite there yet. The first thing we're going to do is we're going to look at create server, because that's where we start to listen for clients connecting. So here it is. And the first parts of this are pretty simple. We create a socket. So let me first orient you where you are. You are now a layer beneath the example application. We are in the standard library itself. We're looking at the implementation of the event loop in the Async IO module in the standard library. And we create a socket, we bind it to an interface, we listen on a port. This stuff is not specific to async, so I've just kind of ellipsed out the details there. The interesting stuff starts when we call sock.setBlockingFalse. Making a socket non-blocking means that all operations we attempt on the socket are either going to succeed or fail instantly, but they'll never block. So whereas on a normal socket, you would call sock.receive to ask for some bytes, and if there aren't any bytes, waiting to be received, then you block. With a non-blocking socket, under those circumstances, we would raise an exception. So the next thing we do after that is we get the socket's file descriptor, and we pass it into the selector. And the selector is magic. It's part of this magical selectors module that we're not going to talk about. We're not going to describe how it works, but we are going to see what it does. And what it's doing here is it takes a file descriptor and it takes an event mask, which is the list of the kinds of events that we're interested in. And in this case, we're interested in when the socket becomes readable, because that means that a client is trying to connect to us. We also pass in that third argument, which is any data at all. The selectors module will accept any data that we want to pass in, and then we'll get that data back out later if the event that we're interested in occurs. So in this case, we're passing in a tuple, and the tuple is the reader callback and the writer callback. And the writer callback is none because a listening socket is never writable. But the reader callback is a new method on the IO loop called accept connection. So we've created a listening socket. We registered a callback to be executed when somebody's trying to connect on the listening socket. And now we can look at what's in that callback. So we're going to look at the implementation of accept connection. So here it is. This is the second of the methods on IO loop that we're looking at. And first, it calls accept on the socket. It knows that there's a client waiting to connect to us, so it knows that it's time to call accept on this socket. And the return value of that includes a new socket called con, and that represents the new connection to the client. And since it's a new socket, we have to call setBlocking false on that too. Then we instantiate the protocol by executing the protocol factory. And the protocol is that chat protocol that we saw implemented in the example application. Finally, we wrap up the event loop and the client connection and the protocol, and we stick all of that into a transport. So we're almost there. And we're going to see how the transport finally completes our goal of executing on connect. So the socket transport's init function is here. It takes the loop, the client connection, and the protocol. It calls its superconstructor. And then look what it does at the bottom there. It calls self-protocol connection made. And that was actually our goal. We wanted to see how a client connecting to us caused that method called onConnect to get executed. And here you can see that we've called connection made on the protocol. That makes another function caller too. And it calls onConnect, which is what we wanted to see. So does that mean that we understand how async works? Almost, but not quite, because there was a detail that I sort of glossed over, and it's this. We saw how we passed accept connection into the selector as a callback, but we didn't see exactly how the client trying to connect to us caused that callback to be executed. So in order to understand that last piece, we need to rewind all the way back to our example application here. We saw create server and the chain of events that it leads to, but we didn't look at the final line, loop.run forever. So let's look at that. Here it is. and now we're back in async IO. We're back in the standard library. This is the third event loop method that we've seen. We saw create server and accept connection, and now this is the third and final method we need to look at, run forever. Now, as you would expect from the name, run forever is an infinite loop. While true, it receives an event list from the selector. And as with everything else with this selector, this is magic. We're not going to see how it works, but we can see what it does. It returns a list of events that are currently ready on non-blocking sockets. So we iterate through this event list, and each item in the event list is a file descriptor, a bit mask of pending events on that file descriptor, and also the data that we earlier passed in. So the data, remember, is the reader callback and the writer callback, so we unpack that from data. And then we check, is the readable bit set on the event mask, and is the read callback not none? If so, then we don't actually execute the read callback. We add it to a list of pending callbacks. And then we do the same for the write bit. We check if the write bit is set on the event mask, and if the write callback is not none, and if those two things are true, then we add it to the ready queue. Once we've processed the whole list of events this way, we have a ready queue full of pending runnable callbacks. So then there's this sort of funny and not very Pythonic looking loop at the bottom there where we check the length of the ready queue, and then we pop callbacks off of the ready queue and execute them. And the reasons why we do it this weird way, you might think, like, why not just run all the callbacks in the ready queue? A callback can do anything, and that includes adding new callbacks to the ready queue as it's running. So we don't want to run those secondary callbacks now. We only want to run the callbacks that were ready when we reached the top of this loop. Any callbacks that they register and add to the ready queue will have to wait until we've reached the next iteration of the whole event loop. And this guarantees certain things about scheduling and starvation that async IO wants to guarantee. But we don't actually have to understand all that. Here's what we do need to understand. We earlier registered for event notifications on a listening socket, and the reader callback was self.accept connection. So here we are in the event loop. When that listening socket becomes readable, we get the event for that socket from the selector. The callback is accept connection. And that's what we wanted to see. We wanted to see how that got pulled back out of the selectors module and executed as a consequence of a client trying to connect to us. So now we've seen the whole thing. And for visual learners, we can go through it again with boxes and arrows. So first we saw the application start up, and it called start server on the event loop. And then the event loop registered a file descriptor with the selectors module and passed in the accept connection callback. After that, we returned to the application, and we saw the application call run forever on the loop. And then the loop saw the event on the listening socket, and it pulled the callback out, and it executed it. And that callback, in turn, called back into our chat protocol implementation and executed on connect on that. So now we've seen the whole chain of events, and we've seen at a very low and basic level how async actually works. So to review, async IO, it uses non-blocking sockets, and it registers for event notifications on those sockets using the selectors module, which wraps the ePoll or KQ facilities. The event loop knows about all of the non-blocking sockets in the system, And when events occur on those sockets, the event loop executes the associated callbacks so that your application can run its application logic in response to those I/O events. And now that we've kind of gone like, when should I use it? What is it? How does it work? And then we've gone back to what is it? Now we can do a final review of when should I use it? So like with medicine, there are indications and contraindications for async. Indications in favor of async are pizza. So if you have a web application with some kind of backend that you're spending most of your time waiting for, rather than spending most of your time doing computation, that's a good application for async. Additionally, if you have sushi, if you're doing WebSockets, that means that you're doing very little computation for each open WebSocket connection, but you have to have a very large number of them idle at a time. So async allows you to minimize the memory that you spend waiting for events on those WebSockets. And basically, any time that you have a very large number of concurrent connections, but you're not spinning very much CPU, handling client requests on each connection, that's a good application for async. Contraindications are when you want a submarine sandwich, when you're doing computationally intensive work. In that case, async doesn't win you very much because you're not doing very much I/O concurrency. You're better off focusing on CPU concurrency, so the additional complexity of async doesn't win you anything, so it's best under these circumstances not to use it. Another issue that a lot of people get wrong is they use an async framework, but they're talking to a database with a synchronous driver. So if you're using a blocking driver with an asynchronous framework, you're blocking your event loop whenever you talk to the database. And you're giving up all of the advantages that you chose async for. So with MySQL, for example, people often use it with Tornado, but a long-running MySQL query will have disastrous consequences for your throughput under those circumstances. So you're better off using multi-threading. In the case of MongoDB, I spent a very long time writing a non-blocking driver called Motor, which allows you to connect properly from Tornado to MongoDB, just to ensure that you're able to use an async driver with an async framework. The final issue that you have to deal with is, what if you don't know async very well? And what if now is not the right time to invest in learning it? I would say under those circumstances, you need to be judicious in when you decide to invest the time in learning it. It's unfamiliar, you can get it wrong, the code will look weird to you, so you need to decide that you're going to learn how to use it, and you need to decide when that moment is in the period over which you're creating your prototype or whatever. Don't just launch into it thinking it's going to be easy. And the final thing about this is it doesn't have to be all or nothing. So it's very frequent that you have a big, complicated web application with many kinds of tasks. And some of those, like a chat feature, might best be served by an async service, and some other aspect of your stack might be better served by a conventional multi-threaded server. And that's fine. You just mix and match those in separate processes, and you connect to the proper endpoint for the different features. So that's all I have to say. You've seen what async is, how it works. You've gotten some indications for when to use it and indications for when not. The next thing I'd say to do is read PEP 3156, especially look at the coroutines section of it, because It's really fun and cool, and we didn't get to touch it at all today. And the next time you have a chat application or something else that could benefit from this kind of paradigm, give it a try and see how it works for you. So I think that we have a few minutes for questions. 5 minutes for questions? Great. So are there microphones in the stands, or?
Microphones there and there. Feel free to get up and line up and ask your questions.
Great. Go ahead.
Are you planning to port Motor for Async IO, or any plans in that regard?
Yes, absolutely. It's kind of a problem of priorities right now, both because we don't have a lot of MongoDB customers on Python 3.4 in production, and also because Async IO itself is so novel. But I think that maybe in the next year or two, I'm definitely looking for a way to make Motor kind of concurrency framework agnostic, so that it could work with not just Tornado and Async IO, but also probably Twisted and anything else that comes out of the woodwork.
Thank you.
Thanks.
Hi, thank you for this explanation. It's very clear, and I'm going to point a lot of people to it once it's recorded.
Great, thanks.
And I just wanted to ask if you have any quick advice for debugging this kind of applications, because debugging an asynchronous application is quite different from debugging a traditional application.
Any advice for making them?
For debugging them.
Oh, for debugging them. Yeah.
Seeing what they actually are doing wrong.
Right. It's incredibly hard, as a matter of fact, because the callback style typically loses your traceback. You launch some piece of I/O, and then your stack goes away. And then eventually the callback is executed and something goes wrong, but you don't know why the callback is being run, because the chain of events that led to it being added to the runnable queue is history. Think really hard. Coroutines are better than callbacks for this because for two reasons. Coroutines keep all of your logic within the same function or within the same stack of function calls. And exception handling in coroutines is relatively normal, where an exception will unwind the stack through a series of coroutines in the same way that it does through a series of ordinary function calls. So emphasize coroutines over callbacks when possible, and otherwise, like, good grief, use PyCharm, use your debugger like pray.
Okay, thank you very much.
Thanks.
Hi. You talked about having an asynchronous driver for the database is needed when you are working asynchronous. What about other kinds of I/O that you need to do that are on the standard library, like email, URL opens, and all that is blocking that currently exists?
Right. So this is a huge problem, is that there are protocols that are implemented in the standard library, like email, and those are the formatting of messages and the parsing of responses is mixed in with the scheduling of I/O. And it would be nice if these things were separate so that you could reuse the parsing and formatting aspects without relying on the I/O scheduling. But right now, that's not really done. So this is gEvent's big advantage, is that it monkey patches the standard library and replaces its I/O scheduling with an asynchronous layer. Without gEvent, we're kind of in trouble. Things get re-implemented over and over and over again. So there's a standard library email module, and then there's a new one that was rewritten for Twisted. There's PyMongo, which is MongoDB in a blocking style, and then there's Motor for Tornado. I think that Async IO in the standard library is going to help fix this by giving us a standard async interface to target, but it's going to be a few years yet before that really happens. In the meantime, there's just a ton of duplicated work. And that's really the answer. Can I take one more question? All right. So you're the final question.
Gosh, that's a lot of pressure.
Sorry.
You said you implemented a async IO database driver for MongoDB.
Yeah.
But it seems really strange to me that you did that as a new database driver. Wouldn't it have been more generally useful to have, well, you could always separate the database driver from your async callbacks using a work queue and using a set of workers or some, like if you had implemented that in a higher layer in the ORM or as a layer above the database driver, wouldn't that have been another solution?
So that may be the final place that we end up. What I sort of found when I started working on it was that PyMongo mixed creating requests with scheduling I/O with parsing the response, and those couldn't be easily untangled without starting from scratch. So I did this hack where I schedule I/O on greenlets, and I arrange for those greenlets to be resumed when the I/O that they're waiting for is completed. And I have a long article about how I did that. It's kind of, it works quite well, and it was a cheap way to get where I needed to go. But the kind of technique that you're suggesting is, I think, is where we all need to head.
Even
in
if
the
you
long run.
used regular threads, you could have kept around a small number of threads for the database to handle those calls.
My thought was that greenlets scale a little better if you have a very large number of pending operations. All right. Thank you very much, guys.